Hello, everyone, and welcome to our technical webinar, A Deep Dive into System Containers. In light of a growing demand to increase the workload density per server or per rack, and at the same time maintaining the cost of service low with minimal electricity consumption, system container technology is a hot topic nowadays and is being explored outside of the traditional mass hosting market realm, with increased demand to tap into custom project delivery and application as a service market, where microservices architecture is now a new de facto standard. Today, our one and only Mike Brome, Senior Product Manager at Virtuozzo and pioneer in container technology, will talk everything containers. We will start with virtualization types overview, comparing different types of containers, application and system containers, as well as virtual machine virtualization from benefits, use cases, and density perspective, touching upon microservices architecture design and deep diving into the sizing challenge and mechanics behind disk and network emulation in virtual environments. And last but not least, SLAs. Server availability allows almost zero downtime. We will present today our ReadyKernel technology and live migration features to build a resilient environment. A couple of housekeeping items before we kick off. The chat will be open throughout the webinar, and we will have one dedicated Q&A session at the top of the hour. And now to you, Mike.
Yeah, thank you very much, Tamara. So let's go directly to our topics to talk about today. So you probably know one of the traditional virtualization types is to run virtual machines on top of bare metal servers. They are usually run through some hypervisor, which is in Linux world nowadays KVM. And inside this virtual machine, there's a guest operating system installed like Windows, BSD, or any Linux distribution. It comes with its own kernel, with a BIOS or EFI, with virtualized devices, with device drivers. And on top of this guest operating system, you can run any arbitrary application. It can be, of course, another container technology like an application container, which is assembled with the help of Docker. Or some standalone applications like a mail server and so on. This is some way of traditional way of virtualization. And on the other side, there's a more resource-oriented or optimized way, which is called a system container. A system container can also run multiple applications inside its container context, but it shares the kernel from the host node. So in container context itself, it can run only a Linux distribution. So you run a Linux bare metal system plus a system container which shares the kernel across all the containers on this host node. Inside this container, you can run again arbitrary Linux applications like a web server like Apache, a mail server, and so on. But you can also run a Docker container inside. This is what we call a nested containerization. So it allows you to use Docker or Kubernetes inside our system container with our kind of isolation and enhanced capabilities like live migration, backups, HA containers on top of distributed storage. Everything can run inside Docker, inside our system container on top of distributed storage. So it gives you a lot of benefits and some enhancements which are Docker or Kubernetes not delivering out of the box, like persistent storage, backups, and migration. On the other side, there's also upstream technology in Linux available called Linux containers. And they are very similar to our system containers, but they come without live migration, without out-of-the-box backups, without live kernel patching, and so on. And then lastly, the smallest subset is an application container, which you are probably familiar with. One of the first ones who built it in a large scale was Docker. And basically, it's an isolation approach for a single application. So you can run a MariaDB, for example, inside the Docker container. You can run Apache inside the Docker container. And all these Docker containers run on top of Linux. And you can typically emulate the LAMP stack in isolated microarchitecture approach. And regarding our system container technology, so Tamara mentioned already that we are here for a long time. So we have more than 20-year history in containerization. So we are a pioneer in virtualization of system containers, and our containers are designed for corner cases. So basically, one goal is to deliver high density to service providers to reduce TCO and costs, and to increase and maximize revenue per physical server. So you probably know that Linux behaves unpredictable if it runs out of resources. So for example, you over provision memory or CPUs or disks. The behavior of Linux is no longer predictable. It can start to randomly kill processes, randomly terminate containers, or in worst case, it could crash or reboot. And our container technology is designed for these corner cases. So when you over provision memory, if you over provision CPU, so all these kind of resources, the behavior of Virtuozzo system containers are predictable. This is the main asset of our system container technology. And this has been invented more than 20 years ago. So a couple of years later, when our technology matured and was in use by several service providers across the globe already, we decided to open source it, and it became available under OpenVZ. This is basically Open Virtuozzo. So it's our patch set for containers, which we maintain for the Linux kernel, which is not fully upstream yet, but we are working on it as an open source virtualization product. Basically, it comes with everything what you know probably from our commercial solution, without backups, without memory and IOPS application, and without management panels. But there's also commercial support available. So if you run it in your infrastructure and operate your business on it, you can still get commercial support for it. A couple of years later, when our technology matured more and the Linux ecosystem grows, we decided to replace our in-kernel live migration and suspend and resume technology with two other technologies running in user space. The first one was CRIO. It's called Checkpoint and Restore in User Space. And basically, it allows you to freeze in user space either a single application or a system container and resume it from this state at a later time. It allows to run multiple architectures. So what does it mean? So you can suspend a container on or an application on x86 and resume this application later on an ARM machine, for example. Why did we do it? First of all, the biggest drawback with kernel live migration is if there is a problem with live migration and application behaves very bad, it could lead to kernel crashes because it runs in kernel context. And this operation usually, if there is a problem, kernel will just crash and you have to reboot. With user space live migration, it's much more simple. In worst case, CRIO will crash and you restart it again, but you don't need to reboot the full machine, restart all containers, and so on. So this was the main benefit of having Checkpoint and Restore in user space. And then a couple of years later, we extended CRIO with live migration capabilities. CRIO itself could do also live migration already. So you suspend the application or container, then you transfer the data manually and restore it on the destination machine. But it's not automated. With the help of p-hole, we automated this way and extended it with iterative capabilities. So iterative here means we can live migrate container with two different approaches. I will explain them later during our webinar. So with pre-copy and post-copy, which is called lazy migration, and so on. Regarding system containers, so why they are still important and play a significant role. So first of all, the biggest benefits, of course, are density. And especially since our containers are optimized for hosting provider and service provider workloads, we optimize them for such use case. So in a typical scenario, everybody probably here knows Plesk. Majority of hosting providers, they sell VPSs or services and give customers access to manage their private server or their server with some control panel, which is mainly Plesk or cPanel. And we test our container patches and our container solution usually against a typical service provider workloads. In this case, Plesk and the LAMP stack. And with Plesk, the density is twice compared to virtual machines running the same guest operating system and the same set of applications and the same Plesk installation. And this is very important. So density plays a big role. For LAMP, on the other side, performance is also much better. So you see it on the right side when you compare the number of containers and or virtual machines, and you see the overcommit and memory overcommit, especially in terms of overcommit, our behavior is much more predictable. And our transaction rate per virtual environment or container is significantly higher. It's also almost twice compared to a virtual machine.
Mike, coming back to the electricity consumption optimization, specifically, how would utilizing containers in an environment help reduce electricity consumption?
Well, it's mainly about density. So when density is, of course, twice, you can reduce electricity also by half. So power consumption and power costs are significantly reduced just because of the fact that the density is twice higher compared to virtual machines.
Thank you. And another question for you before we move on to the next topic. Would you please advise how many containers can be run on a typical server configuration and what the limitations are?
So nowadays, a typical server configuration consists of like 2 sockets with 64 cores and half a terabyte of memory. And with such configuration, we are able to run nowadays 400 to 450 containers. The limitations here comes from the fact that we right now are based on a very old kernel from Red Hat Enterprise Linux, which is based on RHEL 7. And in RHEL 7 kernels, the main limitation for our container density are C groups. Because modern Linux distributions, they use C groups very heavily and they create a lot of them, even if they don't use them and don't need them in future. They are just created because they don't expect that they run in a shared kernel. And due to these limitations with C group version 1, we cannot run, well, actually we can run more containers than 400 to 450, but performance will start to degrade and end user will have some bad experience. Actually, with our next release, which is Virtuozzo Hybrid Server 9, based on RHEL 9 kernel, so we'll skip RHEL 8 kernel completely, we will switch from C groups version 1 to C groups version 2, which allow much more efficient way of searching, of traversal, so container density will be significantly higher. Our aim right now is to run on such configuration, which I explained already, with 2 sockets, 64 cores, and half a terabyte of memory, up to 1,000 containers with the next version of Virtuozzo Hybrid Server.
Excellent. Thank you, Mike.
Okay, and let's compare our containers versus upstream containers, because it's also important. You could probably say, well, I can use upstream Linux containers. They are also great. In reality, they are great, but they are not designed for hosters. So in our case, we of course have our performance benefits. They come mainly from our memory and IOPS deduplication, same as density. So when you can deduplicate IOPS, it's obvious that you can put more containers on such a machine because you save the IOP and they can be used for some other applications or other containers. On the other side, there's no live migration support for Linux containers. You can actually, there exists a way to do this with Clio, but it's not obvious. You need to develop most of the components on your own. And there's no live kernel update with, well, with ReadyKernel anyway not, but there are no live kernel updates. In our case, we ship live kernels, live migration to reduce maintenance costs and maintenance efforts. We have actually built-in backups. So our Virtuozzo backups, we have third-party backup integrations with Acronis and other vendors. We have built-in disk encryption for our container disks, and of course advanced memory management. So you can, with a simple policy, define I want to have density policy to overcommit any resource, or I want to have performance density, performance policy. In this case, overcommit is not allowed, but you can guarantee resources for containers. And of course, we deliver security and maintenance updates for a long time. So it's a long-term supported distribution from Virtuozzo and 24/7 support. So let's dig a bit deeper into container types. I have mentioned already at the beginning that there are two types of containers in our world. So one is a system container and one is an application container. And you see on the left side, in a system container, you can run multiple applications in the same container context. So basically, it means to virtualize a Linux guest operating system, which then run multiple services. So for example, you boot a CentOS or a Debian or Ubuntu distribution, it starts system D. System D starts our services like SSH, mail server, web server, and some other Linux applications. And they give you very strong isolation. So we isolate all namespaces, all the disks, all the accesses, and it doesn't use layered file system by default. So basically you get a virtual disk, and this virtual disk image has an own file system for inside the guest operating system, so inside the Linux guest, and you can do whatever you want with it. On the other side, there's an application container, which is typically used to isolate a single application into some resource set. So you give this application amount of memory, amount of CPU, specific IP address to make it accessible from the outside world, and that's it. This typically runs on a layered file system approach. So on top of your file system of the Linux distributions, and most popular examples here are Docker, VIO, which is another container engine, and so on. And mainly application containers have been invented to build a microservice architecture. And what does it mean? So in system container world, actually everything is like all applications are running inside a single container. It's a monolithic application approach. So when you want to scale it, you need to replicate it to multiple nodes. In this case, let's imagine this yellow piece is our web server here. And for example, if you have a LAMP stack, which consists typically of a web server and MariaDB, and you run short of resources for your web server, but not for the MariaDB, you need to scale out this whole system container and replicate it. But in this case, you replicate also resources which are currently not short. So you still have enough capacity probably for your MariaDB, but only your web server is suffering from a lot of requests. That's why microarchitecture becomes more important. In this case, you put every application into a single container, and you can scale out this single application when needed. In our example with the web server, which is this orange-yellow item here, we will scale out only the web server, put it in behind some load balancer, and distribute the incoming requests across these 3 different web servers. But the rest of the applications, like the MariaDB or other applications which are accessed through this web server, they are just available as a single or 2 application containers, and that's it. So scaling out applications becomes much more efficient and easier. So basically, everyone loves cats. So what does it mean? We take all our cats, and instead of putting it into a single basket, which is no longer being maintainable, and you don't know what cat is below this cat and that cat, we will put all the cats into, so one cat into one basket, and we know where it is, what colors this cat has, and so on. So regarding density, why containers still deliver higher density compared to virtual machines, where technology also evolves a lot during the last 20 years? So first of all, you see in a virtual machine, you have a guest operating system footprint. This red thick line. It's definitely thicker than in a container because you need own guest operating system, you need virtualized drivers, and all these drivers, they consume memory, they require some CPU cycles, and so on. So that's why guest operating system footprint is higher. And then, of course, inside the virtual machines, there are resources assigned. Like there's a VM with 1 GB of memory, but only a small fraction of this memory is used. Like in this case, for our third VM here, it's maybe like 20% of memory which is used, but the rest is assigned. And this is usually these assigned resources cannot be used for something else. You can tweak it or tune it with the help of KSM, for example, which is kernel same page merging, where also these free resources become available. But in this case, they are then not guaranteed, and it's not easy to scale down this virtual machine on the fly. While in a container, you can easily adjust these resources whenever it's needed. So you can scale up, scale down on the fly. So basically, you never waste any resources. You can assign what you use, and what is not used will not be assigned. You can just make it available for other containers. So other applications can reuse available resources all the time without any maintenance efforts or resizing operations or management of virtual machines and so on. So what does containers solve in this case? Actually, mainly the right sizing problem, because there are typically two scenarios, over allocation and under allocation. In over allocation, this usually leads to very inefficient utilization of infrastructure and in overpayment of resources that you never use. Like in this example with the fish. It's a very small fish. It has the fish has a lot of water, but probably doesn't need it. But you need to pay for this water. And on the other side, with under allocation, you have a very big fish, which has no space to do something. And this usually results in a resource shortage, which causes performance degradation, performance issues, even downtimes and crashes for all your projects, all your applications, and end user experience will be very, very poor. And in worst case, you will definitely lose revenue. Just for the fact of under allocation. So in over allocation, you pay too much. With under allocation, you will not earn a lot because people will probably terminate their contract and look for some other hosting service provider with a better underlying software. Regarding the research limit versus real usage. So you see, in a virtual machine, typically the load profile is not static. So it's dynamic. There's applications, sometimes it needs more memory, sometimes it needs less memory, it frees some memory. So this is a red line here, so it's a dynamic working profile. And imagine this green one is our used memory. We will see that a lot of memory here is free. But there might be situations when you have probably a campaign and you know that in this case you need a lot of memory. Then you typically create a virtual machine based on the maximum memory in worst case this virtual machine will need, just that you don't have any performance degradation. But this memory is then the rest of the time wasted because it's assigned to this virtual machine, and this virtual machine needs probably for 1 hour a day all this memory, and for 23 hours it doesn't need it. In case of containers, this is much more flexible. So you also have the same working profile. So memory, it's not flat, it's dynamic. So sometimes application needs more, sometimes it needs less. But the rest of the resources, they are still available. They can be used by some other containers, and they are consumed by other containers and applications inside these containers. And this brings very efficient usage of all available resources on the physical node. There's never some resource free which is not in use. You can make so many containers that the system is fully packed and fully utilized. and especially for vertical scaling. So vertical scaling in terms of VMs usually means you upsize an environment, you increase memory, you add some vCPUs, you extend disk space. But at some point in time, you need to migrate the applications inside the virtual machine to a bigger one, because you cannot size it much more larger. And also the resize operation will be, well, not slow, but it will be time consuming. And applications inside may freeze for or stuck for some seconds. In case of containers, this can be done very quickly on the fly for all resources, and you can grow and shrink all resources. So why it's important? Actually, in terms of virtual machine, you would probably resize it maybe twice or 3 or 4 times a day. But in this case, if you do it 4 times a day, you have like a 6-hour period in ideal scenario where the container has some static resources. In container world, you can resize it 100, 200, 300 times a day. Whenever it needs more resources, you increase it. Whenever it needs less resources, you decrease it. It's not time consuming. It's very fast. It doesn't require CPU resources for the resize operation. It's on the fly, and it's very easy. With virtual machines, you cannot do this. Well, in reality, you can do this also like 300 or 400 times. But if you multiply this with 300 or 400 virtual machines on a physical machine, this is a very costly operation, while it is not for containers. And for horizontal scaling is pretty much the same for virtual machines and containers. So you spin up another node, you create another container, or you create another virtual machine, you put a load balancer in front of it, and you distribute the load across the virtual machines or the containers. But imagine the case from our previous slide. So when you need to resize these containers and VMs dynamically behind the load balancer, this can be very time consuming and resource intensive for virtual machines, while for containers it's just a simple command which is executed and everything is applied immediately on the fly without any downtime, without any CPU resources which are required for this resize operation and so on. And why? System containers are still very important from a performance perspective. So if you compare virtual machine disk emulation versus system container, first of all, in system container world, it's no disk emulation. We don't emulate something. A system container uses a shared kernel. So the container has to some degree direct access to kernel functions. They are isolated and you cannot do some noisy neighbor stuff, but they have access. So in case of a virtual machine, there is usually a host kernel involved, which runs a hypervisor, which is KVM, which handles disk access to the underlying file system and to the underlying physical disk. And there's a guest involved, which has also SCSI driver, usually it's Virtuozzo SCSI or Virtuozzo block, and some guest operating system with some guest applications. They access it, and all this is managed via QEMU. So first of all, there will be a VM exec, so a context switch between guest and host kernel, which usually involves some interrupts. Interrupts usually block CPUs, so it's a costly operation. For a single disk or for a single virtual machine, it's negligible. Maybe for 50 to 100 also, but for heavy I/O intensive operations, it becomes very important. And in case of system container, there's no interrupt, no context switching involved. Application want to write something to the disk. Okay, this goes to the host kernel. The host kernel has access to the file system. File system writes it to the block device and then delivers it to the I/O stack, and that's it. And acknowledge it back that the data has been written. And it's pretty much similar for network emulation. So in case of virtual machine, there's again a host kernel involved and the guest kernel. This means with the help of the device emulator, which is QEMU usually, there's a VM exit, which is a context switch, and an interrupt involved. Interrupts again block CPUs. So it can be very costly for very, very intensive workloads. And it writes in the following way. So the guest application writes to the Virtuozzo net driver. QEMU takes this request, passes it to KVM on the host kernel, which passes it to the Ethernet bridge or to some Mac VTAP or SRIOV device, and then to the physical device. And in case of a system container, again, we have an application which want to send some data through the network. It has access to the host kernel, so therefore to the virtual Ethernet, then Ethernet bridge, and directly to the physical device. So it's much more performant operation, which doesn't involve a lot of data copying and context switches and interrupts. And especially one of our technology which differentiates from Linux containers, for example, and from Open Virtuozzo, is our ReadyKernel technology, which allows you to deliver live kernel updates. So actually, it sounds very simple, but in reality, it's a more complicated process. So first of all, you need to build a kernel with and without the patch, so that you get a binary and you can build a binary patch. Then you need to find the difference in this binary patch and combine this difference as a separate kernel module. Then we usually package it into an RPM. We test it, that it can be applied without any side effects and without any crashes, reboots. And after this patch has been tested, we deliver it to the customer. Again, it's not always that simple. It sounds very simple, but it is not. Because there are also some limitations. For example, if data structures are changed, we cannot deliver a live patch with ReadyKernel right now. Because when data structures are changed, another module or a function in the kernel can expect the data structure to be the same as before. And this can lead to, again, unpredictable behavior like a kernel crash or reboot. If the data semantics are changed, it's also impossible to deliver a ReadyKernel patch as of now. And the same for init and entry code changes. And what is not a bigger problem right now anymore is if there are no ftrace hooks in some functions. This becomes less and less because it becomes more and more available that these hooks are there for functions. And very invasive changes like KPTI, but it's a very, very rare case because our Virtuozzo hybrid server kernel is based on RHEL 7 kernel, and we use K-patch or heavily modified K-patch to deliver these patches. There are usually no very invasive changes because RHEL kernel stays on the same version. They backport patches like we do, and that's it. And most of these limitations can also be overcome to some degree with patch rework. So that if we look at the source code patch and do some changes and test it again, that's why testing is very important. We can sometimes even deliver patches which have some of these limitations mentioned above. And lastly, regarding live migration. So, you know, I've mentioned already that there is Creo, which is checkpoint and restore in user space, and with the help of p-hole, which does the actual data transfer, we can copy data from one node to another. It works with local storage, with our Virtuozzo distributed storage, but it basically delivers hardware maintenance without downtime. So this is one of the second angles beside density we have in Virtuozzo system containers. So we want to deliver best and greatest density, allow you to over provision any resource and still have a predictable behavior of Linux. But on the other side, we also want to reduce maintenance costs. Maintenance is very important because you need to inform customers about maintenance windows, and some will come back and say, no, I want another window, or please do this later, don't do this now, and so on. With the help of live migration, you can do at least hardware maintenance without any notification to customers. So when you need to replace some CPUs, put more memory inside, you can live migrate all workloads from one node to another, do the hardware maintenance, bringing back this node, and either you migrate back all the containers or use it for new subscriptions and new customers. And also what is possible with the help of live migration, you can load rebalance across different nodes. So imagine the case you have like 2 nodes, and the one node is fully utilized and the other one is free. You can live migrate certain workloads to the second node, and the first one has enough free resources, performance becomes better, and customers are more happy. And of course, it allows you to deliver high availability within hardware zones and within the same data center, even within different data centers. If networks are accessible in both, you can also live migrate between different data centers. There's no technical limitations for it. And in a nutshell, it works in the following way. We have a source node, and on the source node, we freeze the container, get its state, copy the state and memory to the destination node, restore it there, and unfreeze it. And there is, of course, a frozen time. But this is the simplest approach. So there's also a way of pre-copying memory. In this case, system tracks all the memory on the source node, copies it in parallel to the destination machine until the difference becomes minimal. Once the difference are minimal, it freezes the container, copies, gets the rest of the state, migrates the rest to the destination node, restores it, and unfreeze it. And this is one approach. And the second one, it's called post-copy memory, also known as lazy migration. In this case, the system frees container at the source node at the beginning, gets the state of the fastest changing memory pages, moves it to the destination node, restores it, and unfreezes it. The rest of the state is then copied from the source to the destination node in background mode.
So Mike, pre-copy migration and post-copy migration, how to decide which one is right for me?
Yeah, actually, it's a very good question, and we should definitely talk about it. So for pre-copy memory, actually, it's the safest approach. If you migrated it, and once it's migrated, the source node can disappear. So it can die, no problem with it. Container has been migrated already, and it's fully there. But the problem with it is, so the con is it's unpredictable. So iterations may take a lot of times, take a lot of time because we don't know how many changes there are in memory, and it's non-guaranteed. Dirty memory can always be too big and migration will fail. But that's the pros and the cons for pre-copy. So the pro is definitely it's safe, and the con is it's unpredictable. You don't know how long it will take because iterations can be longer and longer due to heavy memory changes. Post-copy on the other side, its main pro is it's predictable. So time can be estimated and you know how long this migration will take. For a single container, it might not be important, but if you need to migrate infrastructure like 400 nodes, time prediction is very, very important, and it's a sensitive topic. On the other side, there are also some cons. Applications can become slow after such migration because memory can be fragmented, and it's unsafe to the degree that if you lose a node during migration, the source node, you need to restart from the beginning. This is the main con, so that it's unsafe, and if source node dies and you restart it, you need to restart this migration, but it's predictable. So
thank you, Mike.
There's also like a simple explanation. If you want to migrate very huge infrastructure, like from one version to another with several hundred nodes, use post-copy lazy migration. If you do it just during daily operations to migrate containers to rebalance workloads and utilization, use pre-copy memory migration.
Now, I would like to thank you, Mike, for another great presentation and our audience for your time and questions. We will be following up with you after the webinar, and please stay tuned for more information on upcoming technical webinars, and feel free to get in touch with us directly. I would also like to invite you to follow our social media pages for more announcements. Thank you again, and see you next time.